So quenching lava makes a rock.
Yeah, so a very glassy rock as well, because it's freezing it basically. So, and they do this in the very high-tech way of once they've put their nice molten sample in a bucket, they just pour some water over it.
I like that. Yeah. It's just like the bottom of the food chain next to the firing spout of lava with their water bottles.
Water bottles.
Catch a bit. Yeah. Welcome to Wonder, the Planet Earth podcast for curious people. I'm Holly Cook, joined as always by fellow Earth scientist Dr. Anthony Reid. And Anthony, today I'm really excited actually because we are looking at Dr. Lucy McGee from the University of Adelaide. Now, Lucy is a volcanologist, isotope geochemist, maybe the coolest scientist in the room right now. Dare I say, one of the coolest scientists we've met, because Lucy spends time looking at what happens when Earth, among other things, explodes. So, Anthony, what's on our mind today?
Lots of things, Holly. But let's start with Lucy. One of the coolest things about volcanologists is that you see people in silver suits, head to toe reflective gear, like creeping out gingerly in towards a lava lake or some sort of fountain of lava and, you know, pulling out bits and pieces of it. And it's always sort of fascinated me that how brave these people are to do that. Why do they need to get access to?
Why do they do that?
Why don't they just wait till it's cooled down?
Yeah, that's a good question. And yet, incidentally, you know, when we get our qualifications as a volcanologist, you know, that's part of the kit. Here's your big silver suit, here's your trowel, here's your bucket. I have to say, I've never done that. Seen lots of videos of colleagues doing it.
So there's not like actually a diploma that you get your silver suit?
No, unfortunately. They should totally
They
do
should
that.
do the silver suit.
No, I have seen a photograph of a whole bunch of people suited up like that. And then I guess their supervisor's just standing at the back in a flannel shirt. And I don't know, maybe there's a hierarchy there. Or why would we need to actually take runny lava? It's a really good question, because obviously a lot of volcanological studies are done on past volcanoes, ancient volcanoes, but sometimes we actually want to know what the volcano is doing in maybe real time, maybe as the eruption is progressing. We might be able to see some patterns in how the composition changes, and that might maybe help us to understand what it might do in the near future. Also, as the lava cools, it is going to change a little bit its makeup. So if we want to understand what's going on as it's actually being expelled from the ground, that's when we need to take the sample.
Right.
Yeah.
How about that?
Yeah, so there is actually a bit
There's
of
a reason, not just...
It doesn't just look cool.
I didn't think, when I asked you what's on your mind, you really had something there.
Oh, yes. First thing I thought, I've got to ask Lucy.
That's awesome. Right, so we take samples of runny lava because in that instant moment, there's a chance it changes from that point. Like, is there gas coming off of it? What does that mean? Yeah,
I mean, I guess when you get something completely molten or a bit of a slurry, I guess, coming out of a volcano, it will change as it starts to cool. So, you'll have gas coming off. You might have vapor, water vapor things being expelled from it. So I guess when you've got the sample there, and usually they quench it, so they pour water on it immediately, so they kind of freeze it in time. It's like a little time capsule of what was going on in the magma at that point when they collected it. So it's really valuable data.
And when we say quench it, we make it becomes a rocket. Does it become a rock at that point?
Yeah.
So quenching lava makes a rock.
Yeah, so a very glassy rock as well, because it's freezing it basically. So, and they do this in the very high-tech way of once they've put their nice molten sample in a bucket, they just pour some water over it.
I like that. Yeah. It's just like the bottom of the food chain next to the firing spout of lava with their water bottles.
Water bottles.
Catch a bit.
So can we clear up a couple of terminological things here, just because, you know, it's important to work out what we're actually talking about. So what's the difference between magma and lava?
Good one.
Yeah, so that's a really good question. So sometimes we just talk about magma just being everything really, and that's not correct. We would consider magma to be everything below the ground, and once it's actually erupted, then we would call it lava. So yeah. So the floor is lava. That is correct. The floor is magma.
Not correct.
Incorrect.
Incorrect.
Yes. I'm going to remember that for my next kid's birthday party.
Wrong.
Okay. Right. So why does Right. So we get lava above ground, magma below ground. Is it the same? Like, why does it get above ground at all? Does it start below ground? Like how do you even generate a magma? Is there a transition point where the magma becomes the lava? Is that the volcanic eruption?
Oh, that sounds almost going into some sort of philosophical realms here. At what point is magma lava? Well, to answer the first question of how does it actually start to get above ground, I guess we're considering something that is partially liquid. It's quite runny compared to the solid rock around it. And so because it is more runny and more liquidy, it's going to be more buoyant than the surrounding area. And so it will ascend because of that. It might also have some gases in it, which help to sort of propel it, a bit like when you take the top off a bottle of Coca-Cola and it sort of fizzes up and whizzes out and you lose half your bottle of Coke doing that experiment. Yeah, so that's sort of how it would start to maybe come out. Yeah, the point at which you would call it lava. Yeah, that's an interesting question.
Yeah, right.
Yeah.
That is the realm of philosophy more than
science.
I
guess as soon as it's sort of maybe on contact with the air, maybe. Yeah, I'm not sure.
Weird.
Yeah, I haven't
But rocks can melt.
Yes.
In principle, right? Rocks can melt.
Which is actually a bit crazy to say. That's how the magma comes about it all. What's melting there?
Yeah, and this is an interesting concept when we think about, I guess, the rock cycle as well, of where you start to melt things, and then as you melt something, you freeze it, and then it becomes something solid, but then you can keep on remelting it and having generations of this. But when we're thinking about creating magma, yes, we're thinking about melting an area in the earth, whether that is a very deeper area of the earth, like in the mantle, or something a bit higher up, like the crust, so just the top few kilometers of the earth, maybe. And that can be done in various ways, but we usually need some kind of maybe heat source. So this could be in maybe something we call a mantle plume, where we have sort of a very hot, anomalously hot area of the mantle. We could have a decrease in pressure. So I guess if you can sort of imagine a tray of jelly and you have two pieces of paper on the jelly and you sort of move those apart, the jelly is going to come up through the center, that sort of experiment. Where we have things moving apart, like at the mid-ocean ridges, we'll get magma coming up due to that pressure decrease. That's a very typical way to create melting. Or we can just add water, which also helps to decrease melting temperatures as well. So that will also create some sort of melting.
But just add water to the rocks beneath the surface.
I guess within a certain sort of depth and pressure range, I guess normally it would take a lot for an area of the mantle to start melting. But by adding water, we can approach lower temperatures where we can start to melt it.
Wow.
Yeah.
So another thing that you see in the movies are things like underground. You go down underground, and then suddenly there's this huge cavern.
Yeah.
And some movies that cavern is filled with water or something like this. So I'm just picturing now. Okay, you've got somewhere deep in the earth, you've melted it.
Mm-hmm.
Does it all turn into one big blob of magma, or what does it actually look like? And I guess there's stages of that as it gets towards the surface. How can you sort of describe that? Let's say we were taking a piece of the mantle, and you give it enough heat, or you lower the pressure, or you add some water, it starts to melt. What does it look like?
So there's definitely places on Earth where we can actually sort of see that process happening. So areas that were once very deep that have now been lifted up to the surface, and it usually looks like a sort of a network of things moving up through it. So it wouldn't be that a whole portion has just become completely liquid and has sort of moved up to the surface. That would make a great sort of apocalyptic film, wouldn't it? Like this moving massive sort of fiery death coming to the surface. But we're really sort of thinking about areas of the mantle starting to melt and starting to become liquid and sort of permeating its way up to the surface. So, and then once it reaches the crust of the Earth, there used to be the mainly held theory was this sort of what's now been dubbed the sort of big tank of magma theory.
I like that.
Yeah, it's a good name. Where you would sort of have a big sort of bathtub shape, basically, of just magma and partially molten stuff. But nowadays, I think it's generally accepted that it would be quite a sort of a stepwise operation, really, that you would have melts start to accumulate, maybe at certain weaknesses, maybe where the base of the crust meets the mantle, where you have a bit of a weakness there. Maybe they would occasionally permeate up and maybe form another smaller little reservoir, and they would move their way up in that kind of way.
Now, the other question I have for you is, what is somebody born in the central parts of England studying volcanoes?
Yeah, how dare they? Yeah.
That's just crazy.
I think when I think of England, I think of a lot of things.
Yeah.
A volcano is not one of them.
Of the things.
Yeah. Well, there's definitely ancient volcanoes
Sure.
in the UK, but most of the work that I have done in my research career has not been on ancient volcanoes. Actually, it really wasn't until I came to South Australia that I started talking about things in terms of millions of years and sometimes even billions of years. I've mostly worked on things that have erupted either in the last few years or the last few decades.
Okay.
So baby rocks.
Yeah,
Baby rocks. So
the birth of volcanoes.
Literally the last few years. So in
Yeah.
times where the lavas have formed in our lifetime.
Yeah, and we have observations of them as well, and they've been documented, and observatories monitor them as well. So, yeah, how did I end up doing this? I mean, I think volcanoes are intrinsically just so interesting, and a lot of us as kids, we just, we love it, and it's things we always wheel out at outreach events because we know that the kids are always going to like dinosaurs, meteorites, and volcanoes.
Yeah,
right.
They're like the big three.
Holy trinity of geology.
Yes. Yeah. So I always loved volcanoes. I was very lucky to have a really excellent lecturer at undergrad who was a volcanologist, very much a sort of classical volcanologist who went and, sampled lots of things out in the field. And I was lucky enough to do my honours degree with him, and he sort of, just showed me the potential directions I could go in, and I made contact with some researchers at the University of Auckland in New Zealand and applied to work on one of their PhD projects about the volcanoes in Auckland, and was lucky enough to get accepted to that project.
There are lots of volcanoes in Auckland.
There are. I think at the last count, there's 53.
Oh my gosh.
It's gone up since I started doing my PhD. It was 49.
Because one's formed, or they've
Well, yeah,
or they've
you'd
just
think that.
discovered a different one.
They keep just discovering more, really. So every time there's something sort of vaguely round in the landscape, it's, whoa, is that a funny field? Is that another volcano that we didn't, Yeah.
How do they know if it's a volcano? So if you just look at a mound in the distance in Auckland, what about the mound makes you realise that you're looking at a volcano rather than just another hill?
Yeah, that's a great question. I guess volcanoes of that kind in Auckland, that we call them monogenetic, which means one genesis, they appear to have been formed just by one very short-lived small event. So they generally mostly have come up one vent, and they form a very circular structure.
Right.
So I guess if your hill is very circular, usually only sort of a couple of 100 meters high, it's quite difficult, I think, in something other than a volcanic eruption to get something very circular. So you'll notice that any lake that is formed by a volcano is beautifully circular. Glacial lakes don't look like that. It's so very circular things for sure. If you have any kind of rock outcrops nearby that you might be able to sort of scrubble into the dirt and sort of see if it looks very volcanic, and, if it's got lots of holes in it that might, look like stuff that had been ejected with lots of gas and things, then that could be potentially evidence as well.
Right. So eyes open.
Correct.
Round
Maybe
hills.
The 54th volcano in Auckland.
So that was where you did your PhD.
Yes.
And then you went to...
Then I went to Chile for 3 years. Yeah, so that was a postdoctoral position, which initially was actually not particularly working on active volcanoes from using my background in volcanology. It was actually, I was going to be working at a geothermal centre.
I see.
But yeah, just research projects sometimes change over time. And I ended up getting a grant to look at baby volcanoes down in the south of Chile. So small, very overlooked volcanoes sometimes that sort of live adjacent to the big, more picturesque kind of postcard volcanoes that you see in Chile. So I was interested in why they were there and what connections they had to the bigger volcanic systems.
There's a connection between Chile and New Zealand because they both sit on the Pacific. kind of plate, right?
Yes.
So are they the same type of volcanoes you're working on in New Zealand versus the Chilean ones?
Some of them, yeah. The ones I did in Auckland, the ones I looked at in Auckland are actually very different, despite sitting on very close to an active plate boundary, which is absolutely what Chile is on. They were intraplate, so they are rather enigmatic in Auckland. We still don't entirely know why there are volcanoes there, why magma is being generated. So that's still a really interesting feature that's definitely still being investigated. But the Chilean volcanoes are all very much more of the explosive type.
Ooh,
yeah,
fancy,
yeah.
dangerous as well.
Yeah.
Before we get into the, because I want to understand big explosive volcanoes, but Lucy, so I'm just really interested in what you just said about not necessarily 100% grasping why there's volcanoes in Auckland. How well are you able to, I'd imagine you'd want to predict, like try and understand when these things are going to go up, especially when humans are nearby. How well do you need to truly grasp why there's a volcano there in Auckland in order to try and provide some kind of geohazard insight into the area?
Oh, that's a really interesting question. So why is it of benefit to understand why there's volcanism if we know there's volcanoes there anyway? Yeah, that's a good question. And there's something they actively monitor the Auckland volcanic field. There's, seismometers under quite a lot of parts of various parts of Auckland. The last one to erupt was only 500 years ago, which is really, really not long ago. I guess if we understand the overall genesis of the field, that might give us some kind of understanding of maybe where to expect the next one. In subduction zone volcanism, so active plate margin like we see in Chile, you'll notice if you look at a map of Chile, they're all pretty much in a line north-south. So they're in a sort of predictable location in some ways. When you have this kind of very sporadic volcanism like we see in Auckland, it's a bit all over the place. They can erupt anywhere. So if we understood a little bit more about why there is volcanism there, we might be able to maybe restrict the area that you can expect volcanoes to pop up.
What sort of tools are you using to understand these volcanoes?
Lots of different tools. Volcanology now is very much a multidisciplinary field. And I think that's really wonderful because probably back in the day, it was very much outdoorsy people. This
people
is the
who
thing
want to
for
put
you.
on suits with buckets.
Yes, exactly. Get your bucket out. It was very much a very physical sort of, go out and map and take all these samples and understand the physics of the eruption. And that's still a very important part. Sure. But there's a place for, I think, so many different areas of data collection that feed into all of this now, which is wonderful. So not just the sort of what we would call the physical volcanology, which is really studying the physical aspects of the volcano. It's very much the chemical side as well. So can we look at the chemistry of the eruption? Can that tell us something about what's happened to the magma as it's come up? Also things like the geophysical aspects of the eruption. So people can use geophysical things like magnetotellurics, which shows them maybe where there might be areas of molten material underneath one of the underneath maybe an active center. Also things like, for example, on Mount Ruapehu in the centre of New Zealand, which is an active volcano, has a ski field on it. It has, very adventure sports taken to the extreme.
Skiing down a lava field.
I know, how cool. How cool would you feel?
With the lava chasing.
Yes. It has a lake at the top.
Joking.
And they monitor the temperature of that lake, for example. So that sort of monitoring of things that you maybe wouldn't necessarily think of straight away. They look at the temperature of the lake, because obviously a lake heating up might mean that there is something hot coming below, but a lake suddenly getting quite a lot colder over a certain period of time could also be considered a potential future risk, because maybe it means that there's something plugging the vent, which if the system is still very active, would build up the pressure. So there's a lot of things that I think go into the monitoring of these kind of systems.
Wow. And so the different kind of volcanoes, right? So there's the ones in Hawaii that you could probably this is a simplified thing in my head, but maybe run next to the lava. Not that I'd encourage it, but then you have huge, explosive, wild eruptions. Why is there such a difference? And like, is it? I just think about the rock smelting. Like, what is it? Is it in the lava? Is it in the environment? Why are these so different?
Yeah, very different. Partly, the main thing really is their composition. And by composition, we mean how much silica is in the magma, because the silica creates really the viscosity. And essentially, the more viscous a magma is going to be, the stickier it is, the harder it is to get out of a vent, and the more explosive it's likely to be.
Right.
Whereas the least viscous something is, the more runny it's going to be. It's going to be quite easy to erupt and release its gases at the same time. So you can end up with, a very big sort of spectrum of eruptive styles, from the runny kind of, take a picture of it.
Yeah, just don't get too close and peace out.
Right the way from, run for your lives. Kind of explosions.
So where have you been in and around some of these ideally never in an eruption, but have you been in and around some of these super explosive volcanoes?
Yeah. So I was very lucky a few years ago to go on a field trip in northern Chile, where Chile is a really interesting place geologically. And in the north, there is a very big, thick section of the continental crust. And as you go further south, it goes very, very thin, reasonably thin. And so it's much harder to push magma up through very thick crust. So the sort of magma that you get in northern Chile is usually very thick and sticky and viscous compared to what you get in the south. So the magmas that are forming in northern Chile tend to be ones that create the very explosive eruptions. So they have a large amount of calderas formed by super eruptions, and super eruptions are defined as having emitted a certain sort of cubic kilometers of magma.
We're talking cubic kilometers.
Cubic kilometers, yeah. So there, in northern Chile, there's a beautiful rock that was formed from one of these super eruptions. It's a type of rock called ignimbrite, and it's this beautiful sort of pale pink. And it is so abundant that, when you go up there in all the villages, all of the buildings are made out of that.
Oh,
it's so abundant. It's beautiful rock. Yeah. Really, really lovely.
I love seeing that when you go to different places and you take note of how the something like the homes and houses are constructed out of different parts of the landscape. And it's like you're living and breathing the earth history that has been there. We've really live in it.
And it makes you think, oh my goodness, this is a lot of volcanic rock. If there's enough to build like an entire village out of it, this was a pretty big eruption.
Huge.
So yeah, I did bring in a few little pet rocks you from these areas, if you would like to see.
Yes, they've just been like quietly there.
Waiting for their moment.
Let's do it. What have we got, Lucy?
So this is an example of one of these very sort of sticky, viscous rocks. This is a sort of an ignimbrite. And this is from northern Chile.
So what would it have looked like? So now it's frozen, right?
Yes.
But when it was forming, what would it have looked like? What sort of what would we have seen if we stood there when this thing was erupting?
Your life would have flashed before your eyes, probably. Yeah. So ignimbrites are
very
formed,
briefly before you went extinct,
flattened by this. So ignimbrites are formed from pyroclastic flows, which you can see on any kind of wonderful YouTube channel of volcanic eruptions.
Things about pyroclastic flows.
Yeah. So these are basically where you get the eruption and it creates these huge plumes above the volcanic vent. This is all pieces of rock, loose crystals that have crystallized.
Loose.
Yeah, you can feel that it's very sort of gritty, ash, maybe pieces of just the local rock that have been ripped up as it comes through the vent, all sort of as a swirling cloud. And that's obviously very dense and heavy. It can't stay in the air forever. And it will fall back down to the ground and create a sort of a gravity-driven current that can go sort of, 100 kilometers an hour.
Oh, gosh.
And so these things, they sweep through and they leave these deposits, which eventually will sort of become a solid rock, maybe through the heat of that ash cloud itself.
So how hot can that ash cloud get?
Oh goodness, that's a good test of my knowledge.
Are we talking like 50 degrees or in the
hundreds? In the hundreds for sure.
Right. No, I don't need precise numbers. I just need to know, like, are you baking a cake in it, or are you like it's
hundreds probably hundreds. Yeah.
Right. So ignimbrites, really, really intense.
You can also see little, like the particles in here kind of have a layering to them. Yeah. So this is part of that, indicating that this has a flow to it, right?
It could be either from that flow with it sort of coming down the mountainsides or coming out. This probably more likely was from one of those big caldera eruptions. So it would have sort of been ejected out from maybe the sides of a caldera, but it could also be from just the weight of the eruption. When you've got a big pile of this stuff, it just sort of falls into a pile.
Being compressed by its own.
Yeah.
So now there are also very obviously dark minerals or dark bits and light bits. So why is that?
Yeah, so there's some beautiful features in that
There
rock.
really are. This is quite spectacular.
Of clots. I do like the term clot where we're talking about crystals and things, because it sort of conjures up this image of sort of blobs of stuff all stuck together, and that's kind of what they are really. What's really cool about this is that those are probably really like the dregs of the system that have been dragged up. So quite sort of primitive material that's maybe only just made it, up from the mantle, that have been sort of pulled up as part of that eruption. So it could well be that those little chunky clots of dark material were the thing that maybe even triggered that eruption, that they were the stuff that was input at the last minute, that was, the straw that broke the camel's back and made that thing just erupt potentially.
So I'm picturing that you have some sort of, so we talked earlier about in the mantle, you have kind of very diffuse little networks of melt, of molten rock. That kind of migrates under pressure up into higher crustal levels, but it sounds like there is actually some sort of chamber process.
Yeah.
And how deep do you think, or can we know how deep these chambers might be?
Yeah, so we can, using these sort of multidisciplinary approaches where we maybe look for individual crystals, we can start to analyze them and look at their chemistry to understand what sort of depth they would have been quite happy to form in.
Yep. This is because the chemistry is a result in part of the pressure in which this chemical, because it's all a chemical reaction.
Yes. And there's definitely some depths and stability areas where some minerals are just not happy to be.
Yeah, they can't.
And they're really good indicators of, well, we know it can't be, below this certain depth or above this, because we wouldn't expect to see this particular crystal here.
So we have some type of lava, or sorry.
Hey, we've been through this. We've been through the philosophy. We have. But I make fun of you, but I really want to hear what you have to say.
No, it's a mistake. I misspoke. So you have a magma, sort of, we call them chambers, right?
Yep, or reservoirs.
Reservoir is a nicer word. Okay, we have a reservoir of magma. Yep. And you're saying that there's some type of injection into that of another type of magma, which is somehow triggered that. Is that a change in pressure? Is that a change in chemistry? What is actually triggering that to be erupted? Because otherwise,
true. Why does
the
it come
chamber
up?
is
it's just down there happy.
Yeah.
Why does it get unhappy?
Yeah, so eruption triggering it's obviously a really important thing, because we need to understand what does make them become unhappy and start to sort of ascend to the surface. And usually this idea of there being reservoirs down there of happily sort of stagnating magma that eventually over time, if it doesn't erupt, will become something like a beautiful granite, maybe something with big chunky crystals that isn't going to erupt. The idea is usually that you need some kind of perturbation to overpressure the system, and that could be just volume. You just put too much volume into the system, something has to break to get out. So it could be just bringing new magma into the system, which could be maybe some of those little dark clots there.
The clots are cool.
Yeah, they're pretty shiny and nice. It could be pressure in terms of maybe fluids or gases being put into the reservoir.
Such a dynamic chemical, physical environment. Incredible.
Yeah, definitely.
While we have a little bit of time left, can you show us the last two?
Yeah, so this is also from a similar area, and I think this is
how cool
this is beautiful. Yeah, this is tasty little rock, this one. So
it has bubbles in it or not?
It does have some bubbles in it. It's very dark.
Very dark.
So this is what we would normally associate with a magma that hasn't maybe spent that much time in the crust. It's ascended from the mantle. It's not really spent much time, and then it's been erupted. It has these white crystals in it.
Quite big, like
they
nearly,
are quite square,
half a centimetre square.
Yeah, which we would normally sort of look at this and say this is a typical textbook andesite. Yes, from the Andes, and it is actually from the Andes. But this is, I think, such a lovely example of where looking in detail and taking the hand sample and observing it, but then really going into detail. And this isn't a study that I did myself. This is one that's been published by the people who took us on this field trip. They actually made, very thin slices and did microscope studies of this rock. And these white crystals are not what we expected and not what we would expect from an andesite. They are something from a system more like this big explosive super eruption. So then you have to start to think, well, how could that happen? How could something coming up from the mantle have something that, is a big stagnated batch of crystals? How do you get those two together?
How?
And how is through magma mixing, really. So when we think about these things coming through the crust, take a look.
Love to see.
It's a lovely one. When we think of things coming through the crust, yes, there's quite a lot of crust to get through, but over time, we are going to end up with piles of crystals that don't get up to the surface, that are uneruptable because they're just too sticky, too viscous. We're going to have lots of failed attempts at stuff trying to get through that never quite gets through. You've got a whole big, mixed bag down there of stuff to interact with. So probably what's happened there is you've got these melts coming up from the mantle, and they've interacted with some of these old crystals that have been there for a long time.
How about that?
And you wouldn't know that unless you really looked in detail at what's actually in there with, microscope studies and
my goodness, with everything Lucy says, it just feels like another layer of just what is going on down there. Another dynamic thing.
Yeah.
So what we're saying is these big white crystals are not necessarily entirely related to the cooled lava that they're now sitting in?
Yeah, potentially not. They might be from something a bit
Friends
older.
of, or...
They're neighbours maybe of the magma there. They're not necessarily the crystals which formed in that particular melt, because as melt starts to ascend through the crust, it will cool and it will start to crystallize, and certain crystals will start to drop out depending on what elements are available in the magma, to what ingredients are available basically to make crystals that will be happy in the rock.
Oh, that's great. So you can literally use these crystals as bookmarks of different activity that's happening down there.
Yeah, definitely. And that's a lot of volcanology now, is combining the field studies with what's actually in the rock, really going to detail in looking what's in it, understanding the chemistry and what should be in there. Is it in there? What's this other thing we see in there? Why is it in there? So, yeah. Goodness
me. We're going to have to hard sell this last one, because all I see is a black rock with holes in it, and I've this ignimbrite and andesite have been pretty good, so we're going to need a hard sell.
All right, you can do it, little black rock. Okay, well, it sort of looks a bit like a face, so I think that's definitely in its favour. Well, does it change your mind if I tell you that this is from Mount Doom?
Yes.
There it is.
Yeah, there we go.
The winner takes it all at the end.
So this is from Ngauruhoe in New Zealand, which was used for Mount Doom in Lord of the Rings in the films. So that already is pretty cool. It has a lot of these crystals in it as well. These are the crystals that definitely were supposed to be in there, but when you can see some of them with the naked eye, but when you look at those under the microscope, a lot of those crystals have this amazing feature that look a bit like tree rings. So you look at the white crystals and you see that there are rings all around them down the microscope. And this is showing us that those crystals are actually, they've gone through a really tumultuous journey. They've had changing pressures, the temperatures changed for them, they've had new magma to contend with, and they've tried to adapt to those new conditions. every time something's happened. So as that magma has made its way through the crust before it was erupted, and that's an example of a volcanic bomb, actually. So that was grown out of Mount Doom. Those crystals are recording all of those little intricate changes.
This is a very black-looking rock. It looks a little bit bubbly. You can see little holes in it, and occasionally you see a couple of white little crystals which are probably 2 millimeters across. Some of them are kind of angular, some a little bit more pointy. What an amazing thing, how much Lucy can read, how much she can understand the process that led to it just from looking at it. But then when you take that next step into chemistry, physics, mineralogy, there's so much information encoded in these little...
Yeah, and that's just one rock. And
one
rock. How many rocks there are.
There's a whole Mount Doom mountain of rocks, and this is just a little piece.
Amazing, Lucy. Thank you.
Unbelievable. Thanks for your time, Lucy. Thanks for bringing in such incredible rocks. I just echo Anthony. I can't believe how much you can tell about Earth's interior and what's going on under there based on rocks that look so different and with so many beautiful little features. And one very aptly named Mount Doom rock to tie it all together. Thank you so much.
Wonderful.
Thank you.
It's a pleasure.